Hello, my name is Adam Boss, and this is my first lab for Physics 2 at Georgia Tech, charge tapes. In the introduction, the purpose of this lab was to determine the excess charge on a U-tape by monitoring its interactions, specifically its displacement, or the distance between it and another positively charged piece of tape, and as well as its interaction with gravity, specifically when it's at equilibrium. The main principles that are covered in this lab include Coulomb's law, the electric field, force due to electric field, force due to gravity, and as well as Newton's second law, specifically the momentum principle, which is used to understand the correlation between the vertical forces present in the free body diagram. Now, the models and the formulas that were important for this experiment include the free body at equilibrium, which explains why the piece of tape is at rest between the forces of gravity and Coulomb's law. Coulomb's law, which is of course the product of two charges and Coulomb's constant over the distance times the unit vector, as well as the universal law of gravity, which follows a similar formula with between two masses, a constant, as well as being divided by the distance times the unit vector. And in understanding the relationships between gravity and Coulomb's law, as you'll see in the experiment, when the tape is at rest, there is no change in momentum, which means the net force is zero, which means the force of gravity is the same in magnitude as the force due to Coulomb's law, just in opposite direction, of course, and as well as a force on a point charge due to an electric field, because the tape is considered to be an electric field. So the tape is considered to be a point charge, which is under the assumptions. The tape itself, both of them are considered point charges because the charge is actually dispersed throughout the entire pieces of tape, but it's easier to make calculations assuming it's a point charge, specifically with the limited physics knowledge we have. And we also assume that the distance between the two tapes is uniform to make calculating the distance in the vertical direction simpler. There could be inconsistencies in the pieces of tape, which is a possible error I will discuss, but we just assume that the distance was all the same. So in terms of the experiment, the measured length of tape was about 0.21 meters, with its width being 0.18 meters, and its mass 0.000221 kilograms. And for the result of the lab, the distance we measured, which is its interaction, was 0.003 meters. This is when the tape was at rest. Now for the system, this is tape B, or the suspended tape, which I will explain later, and the surroundings is everything including tape A and the earth. So what was done was two charged pieces of tape were prepared. One piece of tape, tape B, was suspended between two objects, stretched perfectly, and then another charged piece of tape was held under it. Its displacement was measured, or specifically the distance between the two pieces of tape, such that tape B is at equilibrium with gravity and Coulomb's law, and knowing the force of gravity, of course, is the mass times gravitation, or times 9.81 meters per second squared times its mass, which is 0.00021 kilograms. You know the force of gravity is also the same as Coulomb's law, so those were held equal towards each other. This was the code that was prepared for the laboratory. This one considered the piece of tape to be a point charge, and in similar fashion, it calculated Coulomb's law and considered the gravitational constant between the two pieces of tape for it to be at equilibrium. The results were somewhat different between the two due to inconsistency in the actual experiment and assumptions that coding made. Specifically, there were similar results between the coding and the experiment, but one of the issues in the coding, as you'll see in errors, is that, or with the experiment, is the possible dissipation of charge, which coding didn't consider. And of course, coding was simply creating a free body diagram between the tape, gravity, and the electric charge exposed to the other piece of tape. In terms of errors, the tape is not actually a true point charge. Charge is dispersed throughout it, but in the calculations, it is assumed that is a point charge. As well, mass could be lost by taping it to the certain sides, because that mass is not necessarily considered in the gravitational formula, because they're in a way supported. It's not that the full piece of tape that was measured in its mass is considered and is exposed to the force of gravity. And then also the distance between the tapes was not uniform. So what if, in the conclusion, if the signs were flipped, nothing would really change. It just means they are opposite. It's just a perspective in physics. For example, left is negative and right is positive, but if those were to switch in physics convention, nothing would necessarily change. It's just how you look at it. It's just important in keeping directions the same. And it's important to minimize contact because the human body is actually a conductor and charge will flow through it. This will cause charge to dissipate and mess with calculations. And so it is important to minimize the contact between the tape and the human body, or else you can cause inaccuracies when calculating.